Hello, everyone. This presentation relates to the Cyber-Physical Systems Security knowledge book. And we're going to talk about the security and privacy aspects of cyber-physical systems, as well as some of the policy aspects. Cyber-physical systems basically started with the modernization of our physical infrastructures. So over the past 2 decades, most of our industrial control systems, the automation of our manufacturing, automation of buildings, the power grid transformed into a smart grid, intelligent transportation systems, all of these infrastructures were modernized by a variety of technologies. Some of the driving technologies at the time were embedded systems, and at the same time the communications with these embedded systems that were mostly wireless, and there were a lot of technologies spearheading this movement, wireless communications in industrial control systems like wireless HART or ISA 111, or standards for wireless communications in embedded sensors like 6LoWPAN and ROLL and 802.15.4. They were sort of like the driving factors for allowing operators of large infrastructures to be able to deploy sensors wherever they wanted and see basically the state of their system in a fast and accurate way. This obviously led to a variety of improvements in also in smart homes, autonomous vehicles, agriculture, and a lot of these things were driven by basically the combination of control, computation, and communications. Cyber-physical systems are basically the intersection of these three aspects. So we've had intelligent infrastructures or infrastructures that are being controlled and monitored for over a century. The power grid has been working more than a century ago. But most of the control and operations of these systems were done in an analog way. So there was a signal that was sent like from a wire, let's say, and an analog signal, and then it got to a system that would take that analog signal and produce a control signal that was also analog. In the last 50, 40 years, some of these changes, instead of analog, they turned into digital. So there was digital control, and where you had to take discrete points of time measurements and then send control signals also in at discrete points of time. And in the last 2 decades, we had the ability to put more sensors and more controls, but at the same time, not have the communication readily available, but like use networks. So this is basically cyber-physical systems are the integration of all these technologies. And the result is that we're having basically interdisciplinary research. So cyber-physical systems combine expertise of people from control theory, people from like networks, people who are experts in cybersecurity. So all of them come together to try to design these systems and secure them. So in a cyber-physical system, you usually have a physical infrastructure that is being controlled, a set of sensors that can be networks or not, and they send the sensor measurements to controllers who can be distributed. These controllers then make decisions, and they send those decisions to the actuators, like a valve or a pump, and thus they, in turn, affect the physical infrastructure. Of course, now when everything is modernized with computers, we also have the threat of cybersecurity, and some of these problems have already been exploited. So attacks to cyber-physical systems are becoming more common. Probably the most, in this slide we have 3 of the most popular ones that we have seen in the past decade. So probably the most famous one is the Stuxnet worm, which is summarized in a book called Countdown to Zero Day. This was a malware that was installed in a controller, in a computer that was controlling centrifuges for enriching uranium, and it was basically trying to damage them. There were also some blackouts in Ukraine caused by cyber attacks, and that one also had a malware that has been named Industroyer. That was basically malware that was trying to communicate with devices in the power grid and turn them on or off, mostly off. And one of the most recent examples of malicious attacks malware for cyber-physical systems is something called Trident, which caused disruptions in some critical infrastructures in the Middle East. So just to give you an example of some of these attacks, what happens is a typical control system has what is called a HMI, or a human-machine interface, that it sits in a control room where an operator gets to see what's happening in their system. And they set configuration points and set points for the system to operate at. So for example, the operator can say, I want the centrifuges to rotate at 1 kilohertz. And they send that information to a computer that is called, most of the times, PLC, a programmable logic controller. And then the PLC will try to send the commands to the actuators so that they obey the desired preferences from the operator. So in this case, they want centrifuges to rotate at 1 kilohertz. So they send that information. They collect measurements from the sensors, and the PLC then sends that information to the control room, where they can see, the operator can see how everything is behaving in the HMI system. One of the problems of, that Stuxnet created was that the operator was still sending me the information that I wanted the centrifuges to rotate at a specific frequency, but the malware was changing or overriding what the operator wanted, and it was basically asking the centrifuges to rotate really fast and then really slow, creating some resonance and destroying the centrifuges that were used for enriching uranium. So the sensors were obviously saying that the status was not perfect. There was some damage going on, but the PLC was ignoring those measurements and sending back to the control room that everything was normal, there was nothing to see here, and the operators wouldn't know this was happening. So this was probably one of the most famous attacks in control systems and industrial control systems in particular, but cyber-physical systems are not only control systems, they encapsulate a wide variety of interactions with the physical world through computer medium. Another set of threat vectors are potentially medical devices that are also being modernized with software and network capabilities or wireless communications capabilities. So medical devices, you have now, for example, deep brain neurostimulators, gastric stimulators, cochlear implants, cardiac defibrillators, and pacemakers, and other devices that the doctor can reconfigure without an invasive procedure. So through a wireless channel, they can reconfigure these devices. And of course, that also creates threats. Some of these devices have shown to be quite vulnerable to attacks. And recently, there was a report that one person was trying to change the parameters of one of these medical devices of the boyfriend to cause some problems. There was obviously also news stories how, for example, Dick Cheney didn't want, the previous vice president of the United States didn't want to have a pacemaker that could be reconfigured wirelessly because he said that this could be attacked. So these are some of the examples that are happening in medical devices. In intelligent transportation systems, you have a lot of communications, for example, also between infrastructure and the vehicles that are moving. So one example is the next generation air traffic control system. It's called ADSB, where traditionally this system has relied on radar, which means that basically there's a physical actuator and sensor in the ground that sends a signal, and then it gets back from the planes a reflection, and then the operator can basically see where the planes are at any given time. So a modernization of this will enable the planes using GPS to report their own position. One of the problems, at least at the moment, is that some of these systems are not authenticated, and like an attacker can, for example, they can either listen to where every plane is at the moment, or they can potentially also spoof some of these communications. So an air traffic controller might see planes where they are not, or might cause problems in there. And this leads also not only to intelligent transportation systems, but to the rise of autonomous vehicles. So autonomous vehicles on the ground or in the air, like drones used for delivery. These systems can also be potentially attacked. There's been like proof of concept attacks against GPS and other sensors that can be attacked through what is called a transduction attack. So these attacks are not necessarily traditional cyber attacks that you compromise software and then override the logic. These are attacks that, for example, for example, autonomous cars use a sensor called a LiDAR that sends laser images or laser signals that get reflected, and then the car can see how far away are the obstacles. So an attacker can be, for example, in a front car with a laser pointer and try to create reflections that do not exist. So it can create, for example, an obstacle that doesn't exist. So this is a physical attack and can have a real consequence. So this is an example of attacks of what is so-called transduction attacks that are described in the textbook, in the knowledge book chapter on cyber-physical systems. And yeah, there has been also some practical examples of some of these attacks. And so just attacks against GPS system have been seen, especially in the Black Sea. There has been reports that tankers, for example, or ships traveling in the Black Sea all of a sudden appear to be in the middle of an airport in the ground. And it's not clear what's happening, what's causing these problems with GPS systems, but people believe there has been attacks against these GPS systems, or potentially like training examples or experiments that have been happening for these attacks. And yeah, when you have some of these attacks in some of the experiments we have been doing, you might have a flight that starts somewhere, and then when you if an autonomous system is using the GPS signal to navigate a space, if you spoof the GPS signal, after a while, for example, if it's a drone, it might think it's in the wrong place and will have to correct the trajectory to the place it believes it has to go, but because if there's an offset, it will land or go to a different place where it's supposed to be. So these are some of the most recent attacks, but a decade ago, it was hard to make, for example, legislators and people to convince them that this was a problem. Like a decade ago, it was before people knew about Stuxnet, before people learned about these GPS attacks. So it was a time where not a lot of people thought there would be attacks against systems like the power grid or physical systems, mostly because one of the problems is that they're difficult to monetize. So at the time, there was a lot of cyber attacks and cybercrime, but people say, well, there's no real money to be made out of these attacks, so what is the driving factor? At the time, in around 2009, there was only one verified attack that we knew about. It was an attack that happened in 2000, something called the Maroochydore attack that happened in Australia. And this was a contractor that was helping modernize a water system with wireless communication, so the control room could send, for example, remote signals to actuators like a pump or a valve. And this contractor was expecting to be hired permanently to keep operating the plant, but he was not hired, so he thought, well, maybe if I can cause some troubles, they will call me to fix them and hire me permanently. So he bought a wireless radio, and because he knew the protocols that the system was using, he was just sitting around in the car sending random actuation signals to start a pump or shut off a valve. And these attacks happened for, I think, more than a month. It was more than 750,000 gallons of untreated sewage water that was intentionally released into parks, rivers, and hotel grounds. This caused a loss of marine life, and public health was jeopardized. And yeah, at the end of the day, because at the time no one was really thinking about these attacks, that's why he was able to do them for a long time, and the operators were actually thinking that this was a malfunction because they didn't expect an attack, but then they finally realized they realized it was an attack. They caught him, and he had to serve the prison time. So yeah, so some of the first questions that we were having at the time, a decade ago, was like, well, how is cyber-physical system security different from traditional computer security? So from a security point of view, experts in security could say, well, I mean, there's nothing really new in cyber-physical systems. It's just applied the traditional security mechanisms or the best practices in security that we have developed for any other field, like the banking industry or the e-commerce industry, and just apply them to cyber-physical systems and everything will be right. And the question is, well, we know that security, 100% security is not perfect, so what happens if an attacker has partial control of the system? Like it has, it was able to compromise a controller, and it can send, for example, wrong signals. What do we do then? And then the security person, well, could say, well, that's not my job then, because that's probably sort of like an operational problem. It should be dealt with people in control. Similarly, people in control, they were not used to security, and they thought, well, security is not my job. This is sort of like the role of IT people, sort of like the operators. And then when we'd say, well, but what happens if you have, if an attacker is already inside and he sends these malicious control signals, then what can we do? And then the response from the control engineers could be, well, that's not new. We already know that when systems or devices fail, we have these engineering principles for fault tolerance and safety that will, like safety overrides or safety interlocked systems that will prevent damages. But one of the problems or the differences is that attacks are different from failures. So yes, it's true that several cyber-physical systems have been designed with safety in mind, so that if there's a failure, you fail in a safe way. But the problem is that these failures assume sort of like a random natural accident. And when you have a strategic malicious adversary, it can exploit those defenses and override them or make them useless. So security in cyber-physical systems is not only about keeping attackers out, but it is also about understanding the risks, mitigating, detecting, and responding to these attacks, responding to adversaries that have this partial access to my system. So in the book chapter, we explain some of these techniques in detail. So for preventing, detecting, and responding to attacks or mitigating the attacks. So the technologies for preventing attacks, they try to focus mostly on either legacy systems or lightweight security principles, high assurance systems, or the idea of preventing this new type of attacks that I was mentioning before, the transduction attacks. So securing legacy systems, a lot of these devices are meant to be to work for about 30 years, like especially these technologies, for example, that operate in the power grid. An asset owner buys one of these technologies and they expect it to work for 30 years. And it is very difficult to guarantee the security of a device for 30 years. So one of the problems is that we always are going to have to be looking at ways to protect devices or technologies that are at some point legacy technologies and you cannot change them. So some of the techniques that people have proposed are, for example, things like bumping the wire. So you don't communicate, for example, end-to-end with the device. You communicate with a proxy that is up to date and with the best security protocols, and that proxy sits next to the device, and then it translates the communication back to the device through a more reliable or secure physical channel. Yeah, it's a similar idea that was proposed for medical devices and also for Bluetooth technologies for privacy was something called a wireless shield. That the idea was that you had, like, for example, the patient of a medical device would have this extra device next to it, like in the keychain or as a bracelet or something similar that would monitor whenever someone was trying to communicate with the medical device, and if a device was trying to communicate with the device that the owner had, it would jam it. And only when for example, when the owner was actively removing, for example, the bracelet and putting it away or turning it off, would someone be able to communicate. Presumably, she visits the doctor. And there's also some technologies for retrofitting security in legacy communication. So how can we sort of like say, well, we have some devices that maybe are up to date and they have to communicate with legacy devices. How can we sort of like maybe add extra packets or extra fields in these network packets that will allow for device security while at the same time being ignored or being compatible with devices that are legacy and do not understand this new update. So these are some of the technologies for preventing attacks. Detecting attacks has also seen a lot of work in cyber-physical systems. There's been a lot of work on remote attestation systems for guaranteeing the integrity of wireless sensors. And the idea is that there's a program in the sensors that would basically verify the integrity and make sure that there's no malicious logic running on top of them. So there's been some debate whether, like, what are the minimal set of techniques or tools that this device needs. Some of the traditional tools for attestation are probably too expensive for embedded systems. So what can we do with without having, for example, extra hardware support? So these are some of the tools that we have seen there. There's also a lot of work on misuse detection, and that has been basically looking at the particular protocols or techniques that are used for in cyber-physical systems and adapting some of the tools, for example, for network intrusion detection to understand some of these new protocols. Like, for example, in the power grid, they might use a protocol called IEC 104 or IEC 61850 to automate substations. And we would need to understand those packets and what's going on to be able to detect attacks. And in the anomaly detection space, there's also been a lot of work into what is called physics-based attack detection. And the idea is that the physical evolution of the system is something that is immutable, and we can have a rough idea of how the system should behave given inputs and outputs. So if the attacker is trying to drive the system to an unsafe place, and if we're able to see that, we would be detecting that this is not something that is consistent with our expectation of the system. And we would be able to detect it. So if an attacker all of a sudden starts sending an incorrect control signal, we can see from the sensors that this is not what it's supposed to be. This is not how the system is supposed to be working, and we might be able to detect that. Or if the attacker sends a false sensor signal, we could see that this is not consistent with the actuation commands we're sending. So we can also detect that. There's also the idea of multiple sensors to be able to correlate what we observe on the system. So, and that would prevent, for example, in the attack that I was explaining earlier, like if you're attacking the lidar of a car to make an obstacle appear in front of it. We can also use, for example, a sonar of the car, and the sonar, if the sonar doesn't report anything, we can report a conflict. So this is also related to this, where we create models of how the sensors are correlated and how they behave based on the inputs to the system, and we would be able to detect these anomalies that are not consistent with the correlations of the sensors and with the control and sensor. And a final technique that has also been proposed is what is called active detection. So the idea is that we not only monitor things passively, but we can also maybe inject a control signal and see how the system behaves. So this can be, for example, if in the LiDAR example, we can send some random behavior in the LiDAR and check if what we get back is consistent with this random actuation that we send. Or in a traditional control system, let's say we are controlling some chemicals in a chemical reaction. If we don't see any changes for a while in the sensor, we might change, for example, the dosing of some chemicals so that we can expect to see a change in the sensors that are related to the inputs that we're giving. If we don't see the sort of like the effect of these inputs, then we can also conclude that for example, what we have been seeing is a replay attack that is not consistent with our control commands. And finally, mitigating attacks. So there's a variety of tools that we can say, well, once we detect, or even if we don't detect, how can we make sure that we operate the system and still be able to survive or operate it in a way that survives the attack? So there's a variety of mechanisms that have been proposed. A lot of them come from the control community, like saying things like conservative control. So, for example, if I do a risk analysis and I think I might be under attack now or in the future, I might use a more conservative approach to control. So usually control systems have safety bounds, and I say, well, how close am I to a dangerous situation? And usually, like for example, in a chemical reaction system, if you have, for example, the pressure in a tank at 2,700 kilopascals, that's the best operating condition. But it's also very, for economic reasons, like let's say that's the way that you create the material that you want to create most effectively. But it's also dangerous that 2,700 kilopascals is also very close to what's the maximum pressure that the tank can have. So if we're close to that one, it's good for economic for efficiency, but it's also relatively bad from a safety point of view because any deviation can cause a problem in the tank, like it can cause an explosion. So a conservative control approach could say, well, based on my current indicators of attack, I may want to operate the system at a less efficient point so that if there's a potential attack, I don't have any damages, but I might be, again, not operating at the optimal point. So that's one approach, and at the end of the day, it depends on the trade-offs between the risks of the attack and your optimal performance. And this relates also to some of the work that has been done on security indices that is trying to basically identify what are the most sort of like vulnerable sensors or parts of the system that can be attacked and cause the most damage. So it's part of the risk assessment of the system. There's also the idea of resilient estimation and resilient control. So the idea is that you might have, basically you have redundancy on the system, and in a cyber-physical system, again, you have a large set of sensors, and you can basically correct some of the incorrect measurements or basically by voting the correct ones override by majority vote, let's say, the incorrect measurements. And this can be formalized in a more theoretical way, like, for example, using an error-correcting code for the sensor signals to make sure that you always get the correct one and the incorrect ones are discarded. That's resilient estimation. Some of the recent proposals include something called inertial resets. So the idea is that if you have a device that is compromised, you might turn it off and reboot it. And the idea is that if the malware was only in memory, it would be erased, and then you would boot up in a safe space. And the idea would be, you reboot and you control the system, and then if somehow you have if you think you're under attack again, you might reboot it again. And the idea is that you might be able to maintain control of the system because the system has inertia, and it doesn't need to have the control signal sent all the time. But of course, that also creates the risk, right, of denial of service attack. So again, a lot of these techniques for mitigating attack, it's a careful act of balancing the risks with the costs and the benefits. Another idea is constraining actuation, the actuators of the system. And the idea is that we can potentially, some of the work we have done is in autonomous vehicles in platooning, we might want to constrain, for example, at what rate can vehicles accelerate. They cannot accelerate at a given rate because that would allow, for example, an attacker to be able to crash the cars. So we would constrain, for example, what the attacker can or cannot do, and that would prevent them from having arbitrary control of the system. We can also keep the system safe even if the attacker compromises a vehicle. The idea of a virtual sensor is also another way of reacting to attacks. One simple idea can be that if you know the system fairly well, you can basically create a simulation let's say for a while you don't trust the sensor, and then that virtual sensor, you will use that virtual sensor as an input to you for your control decisions. This is basically creating what is called in control systems an open loop. So you would be controlling the system in open loop, and that's not ideal because, I mean, you never know what sort of like random perturbations your system is undergoing, but for a short time, I think it can be a reasonable solution to do if you're dealing with malicious sensors. And then there's all sort of like reactive response mechanisms based on game theory, and a lot of work on safety systems and safe controls to make sure that the system is not undergoing attacks. In addition to some of these security threats and security solutions to cyber-physical systems, then there's also the problem of privacy in cyber-physical systems. And I want to start the discussion of privacy, sort of like bringing probably one of the most famous essays on privacy by Warren and Brandeis, who wrote On the Right of Privacy in 1890 in the U.S. And they were basically started their essay based on the right to be let alone principle by the Judge Thomas Cooley. They were describing this the threat of privacy with respect to the new technologies. And in 1890, the new technologies were for things like, for example, a photograph, an instantaneous photograph. It was a new risk for the privacy of people because they allowed the photography of willing or unknowing persons. And they were saying, well, when there's a new technology, we need to adapt and make sure that we're not creating these new dangerous conditions. And I like that example because I think that's very similar to what's happening now, in particular with the Internet of Things and all these sensors that we have like nowadays. So I like this quote by Kevin Ashton, who was recently interviewed by Smithsonian Magazine. He was a British entrepreneur who coined the term IoT in 1999. And he was saying, they were asking him, so what are some of the things that you think are important or unique in this new space of sensing everywhere? And he was saying, well, in the 20th century, computers were basically brains without senses. They only knew what we told them. So basically, the computers only knew what a person would type on their keyboard. And but however, yeah, there's more information in the world that what people can type on the keyboard. And in the 21st century, computers now can sense things. So the GPSs we take for granted in our phones, the lidars in our cars, pressure sensors, there's temperature sensors, magnetic sensors. So there's a variety of sensors that now computers get to see. And that also creates a risk for privacy because consumers are not aware of all the things that these computers are learning. So one of the most popular examples is for example, vehicular privacy. I like this quote at the beginning, a Ford executive that later said that he was misquoted or corrected his statement, but he was saying that we know everyone who breaks the law thanks to the GPSs in your car. Basically, he was saying that because we have GPS in your car and some of these cars are reporting information back to us, we could see what everyone is doing. Yeah. There was a congressional report, but that was asking, for example, car manufacturers, like how much information were you capturing, and they were capturing a variety of information and sending it back. They usually say that it's for better improve the service of their vehicles and understand their diagnostics, but you can infer a lot of things from that information, from the car behavior. There's also the push for nowadays with Android Auto and Apple CarPlay and things like that, all technology companies are also trying to collect information about the behavior, how you interact with your cars, and the question is how much can they or should spy on you. And in cars also there's the car insurance dongles that people presumably will get a deduction in their premiums if they allow the insurance company to collect information about the operation of their car. But the question is, like, what are insurance companies doing with this data and how are they profiting from them? So there are, again, trade-offs between security and privacy in that space. Drones are also creating new privacy problems. There's been various examples of this. One of them was reported about maybe 8 years ago. So the title was, "So this is how it begins. A guy refuses to stop drone spying on Seattle woman." There was a person flying a drone in the second floor of a house and spying on a woman, and the husband came out and say, "Hey, what are you doing? Stop that." And he was saying, "Well, I'm within my legal rights." In the U.S., there's this U.S. Supreme Court case, Florida versus Riley, that says, for example, since airplanes and helicopters often fly over private property, citizens do not have a reasonable expectation of privacy that their activities will not be observed from the air. And he was quoting that decision to see, well, this is bad, this is legal. I'm legally allowed to spy on you. And there's been many other examples of these, like, for example, a father following his daughter with a drone when she was going to school to make sure she was safe. And this other report that, for example, a neighbor was spying on the daughters of a person in a house they had a pool, and then this person came out with a shotgun and shot down the drone. So these are some of the examples that are happening with the drones and privacy. And some of our own work has shown that, for example, if you buy a new drone and you live in, let's say, in a dorm in a university, your neighbor can actually turn on the drone, connect to it, and issue commands to record footage, so it can turn on the drone and start collecting footage in your home. So so these are some of the potential privacy violations or problems in drones. Location privacy, obviously, is one of the things that is most sought by advertisers, and the idea is that they track usually the cell phone, your cell phone. Not necessarily, it can be through the cell phone companies, but a lot of the times they do it with, for example, your Wi-Fi location, like based on how far away you are from the Wi-Fi beacons. And nowadays with Bluetooth beacons, they can also see if you're close to one of the Bluetooth beacons and associate your phone as it moves around, for example, a mall or a shopping district. So there's a variety of tools that marketers can use to track your behavior online. And for example, they can tell a restaurant owner that, for example, 70% of their customers go to this other gym, so maybe you can start selling sort of like gym swag or have gym swag for your restaurant. Privacy violations for children, and this is particularly important because children are easily molded and they accept standards of surveillance, so we need to be careful on what we sort of like present to children as what is acceptable, sort of like norms of behavior. Yeah, some of our work has also shown vulnerabilities in smart connected toys that would allow an attacker to spy, and not only spy on the children when they talk to, for example, the equivalent of an Alexa. So the children would have, for example, a dinosaur that they would speak to them, and the dinosaur will talk to the cloud to get some of the answers. And the attacker could spy on that connection, and not only that, it could also impersonate the dinosaur and start a conversation with the children and ask, oh, what is your name? What does your mother do? Is she out? When does she come back? And things like that. So that can be a bit dangerous. And yeah, smart home, there's a variety of privacy problems in home, from potentially, like for example, determining if the homeowners are there or not based on their electricity consumption, to some of the more recent, some of the examples on for example, even TVs. Some of these TVs also have communications with the cloud, and they originally, for example, the Samsung Smart TV was not sending this information encrypted, so anyone in the internet could listen to the commands that the owner was asking the TV, like increase the volume, reduce the volume, change channel, and not only that, obviously more conversations that would happen in the living room, and that would be dangerous for anyone. So there's a variety of risks that these new technologies are creating, and we need to, one of the challenges is to make sure that consumers are aware of the risks, and they are able to select how to prevent if they are interested in some of these monitoring procedures. Some of the other interesting aspects on cyber-physical systems are related to non-technical components like policy and political aspects. There's two important components in this space. One of the problems, or one of the reasons why a lot of the cyber-physical systems and Internet of Things technologies are vulnerable is that really creating the security, improving the security posture of the system is a hard business case. Making a strong business case for cybersecurity investment is complicated by the difficulty of quantifying risk in an environment of rapidly changing, unpredictable threats with consequences that are hard to demonstrate. And one of the challenges is that, yeah, if you are, for example, the manager of a bank or an e-commerce site, if you don't invest in security, people are going to attack you because that's where the money is, right? And cyber criminals are going to try to monetize the attacks fairly easily. In cyber physical systems, monetizing attacks is harder, and that's one of the reasons that we haven't seen as many attacks to cyber physical systems compared to other traditional IT systems, because it's harder to monetize this. So a lot of the people working in this space, they say, well, security is important, but at what cost? I mean, we're adding security technologies that are potentially not going to improve our security posture because we're not going to be attacked anyways. So yeah, one of the problems is that, yeah, this has led a lot of technologies used in IoT and in cyber-physical systems with authenticated remote connection to devices, unencrypted communications, hard-coded backdoors from the manufacturer. They say they allow that to improve customer experience, but the problem is that if the manufacturer has access to any device they sell, the attacker can potentially also have access, either by working for the manufacturer and getting those secret codes, or by reverse engineering, for example, the firmware and figuring out that there's this, for example, hard-coded key in the device. And one of the problems in there is if we need to, because this is a market failure, so companies in general are not investing enough in protecting these systems. The question is, like, what are the other incentives that we can give them to protect these systems? And the question is, well, maybe can regulation help? So sort of like say, well, from now on, any IoT device that you sell or commercialize in this space needs to follow these minimum standards of security. And there has been a lot of pushback in traditionally from regulators saying, well, if you regulate security like that, you're going to stifle innovation. But at some point, I think the question is if you're going to either have to deal with unsecure devices or maybe try to do the correct type of regulation. In California, for example, there's already been a model regulation to try to incentivize manufacturers of IoT devices to follow better security practices for IoT, so hopefully this will improve the security of these devices. The other sort of like political aspect of security for cyber-physical systems that is interesting, especially in the future, is the one of cyber conflict or cyber war, let's call it. And the fact that pretty much every advanced nation state now has like part of their military dedicated to studying cyber attacks as a way of waging war. So computer networks are basically an extension of the way we interact with others, and any conflict in physical conflict will have its equivalent representation in cyberspace. So far we have seen a lot of cyber crimes, a lot of cyber espionage in traditional networks, but potentially sort of like cyber war or cyber attacks in an armed conflict is something that it's new, and it will obviously involve this cyber physical aspect to it. And there's a question of, well, if we engage in that, what are sort of like the legal aspects of this, and how can we understand the laws of war? And there's an interesting article sort of like discussing this, the international law of cyberspace, the Koch Speed and the Tallinn Manual, that discusses, they discuss this aspect. So the Tallinn Manual is a study of how international law of war applies to cyber conflicts, and the Koch Speed is a State Department speech explaining how the U.S. interprets international law in cyberspace. And the international law by the UN basically says, well, how are nations supposed to wage war? And there's these two statutes that say, well, the jus ad bellum, so what is the right to enter a war, and the jus in bellum, what is the acceptable wartime conduct? And at the end of the day, so the right to enter a war, they say, well, it's potentially we have the right to enter a war if a cyber attack, for example, causes the same damage that a traditional kinetic like a traditional military attack would have. Like, for example, if a cyber attack opens the dams and it creates a massive flood, that would be the equivalent of a missile striking the dam and opening the flood. So that would give us the right to enter the war by this cyber attack. And then there's also the gray area of, well, what are cyber attacks that do not rise to the level of these armed attacks? Can they give us enough justification to enter a war or not? And the acceptable wartime conduct is, once you enter a war, like what are your acceptable ways to conduct it that are in line to humanitarian laws? And the challenges, in particular in cyberspace, are those of proportionality, attribution, and distinction between civilian and military objectives. Proportionality is really hard in cyberspace. So a lot of the times it's really hard to say, well, this cyber attack is only going to affect this infrastructure and it's not going to spread and cause damages in other infrastructures. And attribution is the other big challenge in cybersecurity. So the fact that someone attacked my system and I cannot really tell 100% sure who was the guilty party. So these are some of the sort of like the interesting problems, in particular for cyber-physical system security moving forward in the near future, that we'll be discussing more, and it's an interesting area for research and discussion. So in conclusion, we presented three general aspects of cyber-physical system security and privacy. So for cyber-physical system security, we know that attacks are growing, and that attackers have the motivations, knowledge, and resources, and persistence to launch attacks that will damage the physical world, including humans. We need to be prepared to prevent these attacks, detect them, and mitigate them. The privacy issues are also a growing concern, and we need to design mechanisms to facilitate the utility of cyber-physical systems, because, I mean, we're collecting this data for a reason. It's not that we only want to invade your privacy, but they presumably lead to better control decisions. Like if we collect more electricity usage, more frequently, we would be able to work or operate the power grid more efficiently. If we collect more data of how your car moves in a highway, we would be able to better predict, for example, the traffic flows and manage or plan for future expansions of the car. So we're collecting data for a reason, but the question is, how can we collect the data and at the same time, like for example, collect only enough data that will allow us to get the objective of the cyber-physical system while protecting your privacy. And then there's also this question of the policy and political aspects. So sort of like what are the incentives for securing CPS? So is this going to be solved by the market alone, or are we going to have some sort of like government intervention to improve the security of these devices? We need new international legal frameworks for cyber conflict and how future wars are going to be waged. So with that, I conclude my presentation, and I look forward. Hopefully, you'll read the book chapter on cyber physical system security.